Transactions are the solution to the kinds of problems we've been seeing on the last few slides. Transactions are both a concept for allowing users to specify correct behavior and a set of implementations for allowing a system to achieve that correct behavior in the face of concurrency and failure. Transactions are a major component of database systems and are critical for many, many applications. Arguably, transactions are a bigger contribution in terms of database ideas than SQL because transactions are often used outside the context of SQL. For example, in transactional key value stores, or even in hardware architectures that use things like transactional memory. So the transaction concept goes beyond the implementation of database systems. As an aside, there's been 4 Turing Awards that have been given in the field of databases. The first was to Charles Bachman, who developed some of the earliest databases, including a system called IDS. He won the award in 1973. The second was to Ted Codd, who invented the relational model. He won the award in 81. The third was to Jim Gray, who is the inventor of transaction processing, both the concepts and many of the implementation techniques. He won the award in 98. The fourth Turing Award in databases was given to Michael Stonebraker in 2014 for his work developing and commercializing relational database systems, including the still popular open source system Postgres. So what is a transaction? Well, Gray defined a transaction as a sequence of multiple actions to be executed as an atomic unit. And we'll talk about what we mean by that specifically as we go. From an application developer's perspective, sort of the SQL view of the problem, we specify transactions like this. We have a command called begin transaction, then we issue a sequence of SQL statements, and then we run a command end transaction. And we want that entire set of SQL statements to either all happen or for none of them to happen. And that's what we mean by an atomic unit. So as an example, we might want to transfer money between accounts, and that would require reading one account and updating it, and then writing another account as well. So we want that to be atomic. Another example might be if you're going on a trip and you want to book a flight, a hotel, and a car together and get a package. You want all of those to happen or none of them to happen. So in our transaction model that we'll work with in this class, a transaction is the following. We'll sometimes shorten the word transaction to XACT. It's the database management system's abstract view of an application program or an activity. And all that the database management system is going to see in our transaction model is a sequence of reads and writes of database objects. And that sequence of reads and writes is a batch of work that must commit or abort as an atomic unit. The transaction manager is the component of the database management system that controls execution of transactions. Importantly, in our discussion and in most database systems, the program logic, including the specifics of the SQL query, are invisible to the database management's transaction manager. All the transaction manager is going to see is reads and writes. So there's arbitrary computation that can happen when data is fetched from the database. You can fetch something from the database, do a whole bunch of, say, arithmetic on that data. That's invisible to the database management system. And then you write some data back to the database. So the DBMS only sees the reads and the writes that happen to the database. It doesn't know what kind of application logic goes on between reads and writes. And as a result, we have to reason solely with those reads and writes and guarantee safety for arbitrary computations that could happen on those reads and writes. Now, I'll note parenthetically that there's modern systems that have started rethinking this assumption, but these are mostly research systems, or they're systems that don't have the kinds of guarantees that we're comfortable with transactions. So we'll stick to the transactional model here, and just remember that the transaction manager sees only the reads and writes that are done by a transaction. It doesn't see the SQL queries or any other logic that happens outside the database. So here's a simple example of a transaction from the point of view of the transaction manager. This is a transaction to transfer $100 from account R to account S. It's a sequence of actions. The first is a start to the transaction. Then there's a read from R. Now, R happens to change its value, but the database doesn't see that in step 3. All it sees is a write to R in step 4, a read from S in step 5, and then again, outside the database's view, S is incremented by 100, and then the database sees a write to S and an end transaction. So a transfer happened here of $100 from R to S, but all the database saw was start transaction, read, write, and end transaction.